All right, so thank you very much for the invitation to present some of the work I've been trying to do over the last year. So the talk I'm going to give really fits in very well with the overall theme of the workshop because I will really be interested in studying how these two ideas, modularity on the one side and resurgence on the other, fit in and kind of exemplify each other and make each other more powerful, at least for the particular case of the integrated correlators for the n equals 4 supersymmetric Young-Mills theory. So the overall structure of my talk will be that I will initially discuss some of the background for resurgence in these integrated correlators, explaining why they're physically interesting and some of the kind of mathematical structures which naturally arise, and then I will kind of try and unify them and show how they really fit together. So the first part, I really want to talk about just standard resurgence. So the main idea behind resurgence is, of course, that we have some kind of an asymptotic divergent series, and we want to resum it into an analytic function. So it's kind of a multi-step program where we begin with some kind of a perturbative series, phi p of x, which will be some sum, say k equals 0 to infinity of some coefficients ak, x to the power k. And of course, what makes this series special is that it's a formal series, so it won't converge for any non-zero value of x, but at the same time, we want to bound the growth of the coefficients. We don't want them to grow too fast. So in particular, I will say that their magnitude is asymptotic to some b, c to the power negative k, k factorial. So they have, at most, factorial growth and some subleading power behavior. So the second step of the program is to define a Borel transform. Which is a map which takes this perturbative series and returns now an analytic function, which is a function of a parameter t, which is just defined to be the sum, k is 0 to infinity, a k plus 1 over k factorial, t to the power k. So this will now have some finite radius of convergence, and we can draw it like this. But of course, the point is that there will also be singularities inside this plane. And these singularities really encode the kind of analytic structure, the information these coefficients were originally containing, and they give us a nice kind of function that we can work with. And then the third step is to construct a resummation. So this is a directional resummation, which again, we take in this perturbative series. This will again be a function of x. So you can see that in this Borel transform, we actually lost information about the 0th coefficient. Now that doesn't change anything because really we're interested over here in the singularity structure of the thing. So adding a constant doesn't matter, but we can add it back in. And then we have an integral 0 e to the I theta infinity of this Borel transform, e to the minus t over x dt. Okay, so now we've chosen some direction in the Borel plane and we're integrating from 0 to infinity. And of course, the point is that we can't choose just any direction because some of them might have poles on them or singularities. So there's only some allowed directions. And in particular, as we move, for example, from below a singularity to above it, the two resummations will be different. And as a result, we've kind of traded something which diverged for something which is in some sense ambiguous, but actually this ambiguity is not a bug, instead it's a feature because it actually allows you to extract non-perturbative information about this object. So the kind of final step of the program is to introduce the notion of a trans series, which is a new type of formal object. So phi, which now depends on both a sigma and an x. So it still has the same perturbative piece that we had before, but now additionally, it also has sigma e to the minus c divided by x times a non-perturbative series, which is again some asymptotic thing. And indeed, if this is the closest singularity that sits on the real axis, this point where it sits will be precisely the parameter c, which controlled the growth of these coefficients. So this c is really encoding the position of the nearest singularity, and it's the same c which will appear here in the exponentially suppressed term. And the point is that if I'm integrating slightly below this cut or slightly above this cut, there will be a difference, and the difference will be of this form, so it's exponentially suppressed. And the kind of idea of resurgence is to trade off these two discontinuities, if you wish, one which comes from the presence of this branch cut in the Borel plane, and the other one comes from shifting this parameter sigma. So the idea is that the parameter sigma takes some value sigma minus here, and some value sigma plus over here, and then we require that if I resum this full trans series evaluated at sigma plus above, it ought to give me the same thing as it evaluated at sigma minus below. So over here, I'm kind of in a very simplistic case where I have only a single singularity, and I'm only interested in the small neighborhood of this branch cut. But for the particular applications that we will be interested in today, this is sufficient. So now there's kind of natural questions one may ask when we move to modular functions. So if we now think about modular functions, there's kind of natural questions. So first of all, we might ask, is there an equivalent that is modular invariant? So by this I mean, is there a modular invariant notion of a perturbative series? Is there a modular invariant notion of a Borel transform, of a resummation, and so on? Because really you can think about a modular function as an infinite collection of Fourier modes. So really what you could do is you could do resurgence for each of the Fourier modes independently, and then you can see the exponentially suppressed terms in each one of them. But resurgence doesn't really tell you. Once you focus on one Fourier mode, it won't tell you about all of the other ones. And really the power of resurgence is that it intermixes all of the Fourier modes into a kind of concrete single structure. So really it's kind of redundant to do it for each Fourier mode independently. So we're asking, is there some way how we can really do it for all of them at the same time? Another question one can ask is, do modular functions have resurgent properties? So by this I mean, if I take some random series and just generate some coefficients which have this growth, I'll get some function. I can repeat all of this analysis for this function, but of course what I'll get in the end isn't really in any sense meaningful. So what I'm asking is there something about modularity which kind of enforces that these functions really, that a structure really gives you the correct answer? So for an example, in the original work of Ekal, he really used the fact that these functions come from certain differential or difference equations, and that really gave him the kind of necessary tools in order to prove this. And the third one, question that one may ask, is there some universality to the functions that appear? So by this I mean, there are multiple different physical contexts, and in each of these contexts, the same type of function, dn of s and tau, which I will define later, appears. For example, n equals 4 super Young-Mills integrated correlators, which will be the story that I will discuss. But this very similar types of functions also appear in other contexts. For example, for a ON model, Casimir energy, on a torus times R. And of course, these two theories physically have nothing to do with one another, apart from sharing the modular group as a symmetry. Uh, so, this one is supersymmetric. This one doesn't have any supersymmetry. They're in different dimensions. So it's not obvious why the same function should appear. What I will kind of try to argue in this talk is that really these dn's appear very, very naturally if you try and execute resurgence for modular functions. They're kind of the modular, they're the kind of natural modular non-perturbative completion. So they kind of play the role of these functions. Yes, sorry. Yes, of course, the modular group is a very central theme in both of them, which is, of course, also the explanation for the appearance of these functions. Yes, it's very important. Sorry about that. Yes, okay, so this is the kind of initial background. Sorry. The initial background I wanted to talk about. So now I'll move on to discuss some of the physical background, in particular why these kinds of things are interesting. So second part of my talk has to do with localization and matrix models. So the main idea behind localization and matrix models is that certain observables in supersymmetric theories reduce to finite dimensional integrals. So certainly the claim isn't that all observables reduce to finite dimensional integrals or that these theories are actually matrix models in hiding. Indeed, a lot of the magic of this procedure is finding which specific observables have this property. But at the same time, of course, this is an incredibly powerful tool because in particular, it gives you really access in order to describe an observable in a fully interacting quantum field theory and just get an explicit answer for it. So this answer, this site is both mathematically well defined as well as gives you access to certain types of tools that you might use to analyze it. So it's of high interest. So historically, really, this comes first from idea by Drucker and Gross in 2001, where they were considering n equals 4 theory, and they thought about a Wilson loop in this theory. So their idea is that they take this Wilson loop and they put it here. And, well, it's a conformal theory, so it doesn't matter how big this Wilson loop looks. And then what they do is they send x to 1 over x, which is also a conformal transformation. So it's a symmetry of the theory. And under this transformation, the Wilson loop, which is circular, gets mapped to one, which is a straight line. And then they use a supersymmetry argument where they observe that the expectation value of this Wilson loop is protected, so it's a constant. So this follows from supersymmetry. And so this doesn't look very good for the original observable. It looks like it's under a symmetry gets mapped to something that is constant, but they observe that there is one point which is from which a possible anomaly might come. So a possible anomaly. And indeed, they do some computations and they conjecture that if you take the expectation value of this circular Wilson loop, it ought to be given by a matrix model. So this is a very grand claim, but they don't provide a proof for it, and there's no obvious way how to generalize this construction to either theories or other observables. So the next big insight comes from Peston in 2007. Who really uses supersymmetric localization. So what we will be interested is the n equals 2 star theory, which has the following matter content. So it has a vector multiplet with group G. And additionally, it has a hypermultiplet in the adjoint representation and mass M. And the great insight of Peston is that you can find a certain deformation of this action, which in the limit, which the partition function is independent of, and then in the limit where this deformation becomes very large, the path integral localizes to a kind of finite dimensional one, and they compute the exact partition function, which depends on two parameters, m and tau, where this is the complexified coupling. And it has the following expression. It's an integral over the Cartan subalgebra of some terms. So there's a normalization, which isn't very relevant. And then there's a piece Vg of a e to the minus 8 pi squared over g Young-Mills squared, a with a in g. So this is the killing form. Then there's a Z1 loop piece, which depends on m tau, m and a, no tau dependence. And then finally, there's an instantonic piece, which depends on m tau and a. And you integrate over all of the Cartan algebra, so it's an r-dimensional integral. And all of these pieces are concrete, but not necessarily very simple. So this Vg of a is the Vandermonde determinant. So it will be a product over the roots of the Lie algebra of alpha dot a. This one loop piece is given by some complicated product again, where now we introduce this function h, alpha dot a, divided by h of alpha dot a plus m, h of alpha dot a minus m, all raised to the power 1/2, where this function h of z is given by e to the minus 1 plus gamma z squared times g of 1 plus iz, g of 1 minus iz, where this g is the Barnes G function. So it's a very complex type of expression, but you can go on Wikipedia or DLMF and find some of the properties that this G function has. And then finally, maybe the most unruly piece is this Z instanton of m, tau, and a. And this is the contribution from the Nekrasov function. From Nekrasov partition. At least as far as I know, this doesn't have a kind of uniform expression in terms of the roots of the Lie algebra for a generic Lie group. But again, if you go to specific cases, certainly for small instanton number, you can find very concrete realizations. So the point is, this is a very complicated type of object, but it is a concrete one. So for any particular group of your choice, you can just compute it. All right. So the next question that we have is an observation, which is the observation that if I take this n equals 2 star theory, so it had a parameter which was the mass, what I can do is I can just send the mass to 0. And if you look at the kind of matter that sits inside here, it was tuned very carefully. So for example, with the choice of the representation for the hypermultiple to be the adjoint, so that in this limit, it really goes to n equals 4 supersymmetric Young-Mills, which is, of course, of holographic interest. So really the question is, we start with this partition function, which we know, which we can calculate, and in this n equals 2 star theory, and the question is, how do we get an observable, which is in n equals 4 theory? Yes, exactly. So if m is 0, this Z1 loop goes to 0. It goes to 1, sorry, yes. And the simplest thing that we could do is indeed just set m equals 0, and then what you will recover is that the n equals 4 theory is a constant. Yeah, exactly, the partition function is not a particularly interesting observable. So we need to do a bit more work. And the thing we can observe is that this thing, this partition function, is even in M. And in particular, you can kind of expand it around m equals 0, so there will be a term proportional to m squared, m to the 4, m to the 6. So really the simplest observable will look something like this. So I will define it, Cg of tau. So there is no more m. It's 1/4 hyperbolic Laplacian dm squared log Zg of m and tau at m equals 0. So I'm picking out the m squared term, and this is the simplest non-trivial one. And you know this del tau, you just put it in. It's 4 tau 2 squared d tau bar. So this is the simplest one. But of course, it's not obvious what the interpretation of this observable is in the n equals 4 theory, because we took some derivatives and before setting m to 0. And what you can observe is that we've taken precisely 4 derivatives, 2 with respect to tau and 2 with respect to m. So this is really interpreted in n equals 4 theory. It's really an integrated version of a 4-point function. So it's an integrated 4-point function. More precisely, if I define O2 of x and y to be the trace of phi I, phi j, y, phi I, phi j of x, so trace phi I of x, phi j of x, yi, yj, where this x is position, and these y's are SO6 null vectors. So they satisfy yi is equal to 0. And the purpose of this is, of course, to project down onto the symmetric traceless representation. So this is a primary operator in n equals 4 theory. And then this operator Cg of tau can roughly be identified with an integral over the positions some measure which depends on all of the positions and all of these null vectors of just a 4-point function. So O2 x1 y1 up to some O2 x4 y4. So it's really an integral of some 4-point function. And if you're interested in the specific details of how this comes about, you can see the paper by Chester, Pufu, and other collaborators, which is this 06263. Yes. Mm-hmm. Yes. No, this is protected. This has exact dimension exactly 2. Indeed, that's probably part of the reason why supersymmetric localization works for this specific operator. It's protected. Yes, it's I think 1/2 BPS. But another important thing is that actually the stress tensor is also in this multiplet. So if you act on this operator with a bunch of supersymmetry operations, you will, after I think 2 applications, generate the stress energy tensor. So that's another. Yes, exactly, certainly. So that's what this operator is. This is the n equals 4 interpretation. Oh. Okay. So before I move on, there's one final step I want to discuss, which is, as I already mentioned, the reason we want to get to n equals 4 theory is really because we're interested in holography. So we want to somehow identify this integrated 4-point operator with something via the ADS-CFT correspondence. So for that, what we do is we finally fix the gauge group to be just SUN. And of course, this famously is dual to type 2b strings on ADS 5. That's S5. Okay, so we have an operator on this side. We want to understand what is its interpretation on this side. So if we start with the generic one, where we just take 4 O2s, so this was originally a very complicated function of a whole bunch of x's and y's, so you might expect that it's quite complicated, but it turns out superconformal symmetry fixes pretty much all of the dependence that this operator has. It really ends up depending on just the 2 cross ratios that one can construct out of 4 positions. So it's really just a single function. And remember, the stress tensor lied in the super multiplet. So, and the stress tensor on the boundary theory famously generates gravitons. So really, this will be dual in some sense to the 4 graviton scattering amplitude, which depends on 2 Mandelstam variables S and T. And consequently, once we take the integrated correlator, we integrate over the U and the V. So if you have the integrated correlator, it really gets mapped to an integrated 4-point amplitude. Okay, so this is so we can extract something about graviton scattering completely non-perturbatively by just analyzing this object. Yes, of course. Yes, I mean, really, you can consider it in any limit. The whole point is that this operator is this integrated correlator. I can really have exactly for any value of the coupling and any value of n. So really, it's a fully non-perturbative result, but it's integrated. Yes. Yes, and you will be able to, if you take a certain limit of this operator, which I will discuss. This is even more general. Yes, this works for any coupling at any n, not just in the tooth limit. But you can reduce it to the tooth limit. So one might be interested in multiple limits. The first one, of which is the very strong coupling limit. So in this limit, I send n to infinity while keeping tau, which is theta divided by 2 pi plus 4 pi I divided by g Young-Mills squared fixed. So this is kind of a weird limit. It's not obvious, for example, in perturbation theory that this exists, but it does, at least for this operator, certainly. And if I consider corrections in n inverse, give higher derivative corrections to supergravity.
So for example, r to the power 4, or d4, r4, and so on. So these first two you can actually extract exactly from this limit. They're just the Eisenstein series E3 halves and the Eisenstein series E5 halves, but you get some limited information also about higher order corrections. The second limit one might be interested is the 't Hooft limit, in which one fixes, sends n to infinity, and fixes lambda, which is g Young-Mills squared times n. So in this limit, n inverse is the genus expansion. Of the underlying string theory. And finally, there's a kind of even weirder limit one might consider, which is called the dual 't Hooft limit. In this limit, one sends n to infinity while keeping lambda twiddle, which is 16 pi squared n over g Young-Mills squared fixed. So notice that in the ordinary 't Hooft limit, as n goes to infinity, g Young-Mills is forced to go to 0. But in this limit, g Young-Mills actually is forced to go to infinity as well. So this is an even funkier limit. But in this limit, actually, you have access to non-perturbative effects. Like D-string instantons. And the kind of maybe more physically intuitive idea of why you might want to consider it is that if you start with just the normal theory and you do an S transformation, so you send tau to minus 1 over tau, so that will be like exchanging tau2 with 1 over tau2, and then you do the 't Hooft limit in this S dual picture, this will be what you will get, more or less. And of course, the S duality exchanges fundamental strings and D strings, so that also gives you some physical intuition for why this limit might contain information of that type. Okay, and now I'll move on to the main section. So now I've given quite a lot of motivation, so it's good to see how this motivation is implemented in the particular case of the correlator that I've now defined. So now the third part is we consider integrated correlators. For SUN. So this is a function, Cn of tau. And the first important property that this function has is that it is modular invariant. So if you go back to the matrix model definition, this is by no means obvious, but if you play around with it for some while, you can indeed show that it satisfies this very important property. The second property that it has is that they satisfy recurrence relations. By which I mean Cn of tau is expressed from Cn minus 1, I should probably draw it the other way, from Cn minus 1 of tau and Cn minus 2 of tau. So in particular, Cn of tau is fixed by just the initial conditions C2 of tau and C1 of tau, which happens to be identically 0. So from a field theory perspective, this is incredibly weird, right? Because these are observables in different quantum field theories, but somehow you have a recurrence relation which relates an exact observable in SU2 to an exact observable in SU3, for example. Sorry? Oh, yeah, it is. Absolutely, yeah. It's a very surprising result, certainly. Um, then the next thing we can say is that the Cn of tau actually lies in the space L2F, which is the space of square integrable functions. On the fundamental domain of SL2Z, which is the upper half plane quotiented by SL2Z. So there's a very nice reason for this. There's a paper by Perlmutter and Collier who basically show that this must be the case because this observable must possess a nice perturbative expansion which limits the growth that it can have at infinity. So this is a very generic property that most observables in n=4 theory should possess. Yes, this would be the standard with respect to the standard Peterson inner product. But in particular, because it lives in this space, we can decompose it in terms of the eigenfunctions of the Laplacian. So decomposes in eigenfunctions of delta, which tells me I can write it as a sum of 3 different terms. So the first one is just the overlap with the constant functions. This is just a number. Then there's a piece, which is an integral over real part s is a half of some function of mn of s times the Eisenstein series es star of tau ds over 2 pi I. And then there's still a third term, which is a sum, an infinite sum potentially, over overlaps with things called non-holomorphic cusp forms times the non-holomorphic cusp forms. Now, fortunately for the integrated correlator, all of these overlaps happen to vanish. And that's really a great simplification because these non-holomorphic cusp forms are in some sense quite unruly beasts and they're fairly hard to deal with. Now, this piece comes from the kind of continuous piece of the L2 functions, which are these Eisenstein series. And they can be defined. Yes, they're real analytic. They're not holomorphic. They're certainly not holomorphic. Yeah. For a mathematician, you can take this as the definition because I will write what Mn is in a second. So over here, we have the following formulas. So Mn of S, remember, they satisfy their recurrence relation. Therefore, once I found out what M2 is, I can find out what all of the other Mn's is. And it's actually quite simple in this case. It's n minus 1 divided by 2. Then there's a pi s 1 minus s 2s minus 1 squared divided by the sine of pi s. And finally, there is a 3f2 2 minus n s 1 minus s 3 2 evaluated at 1. So a little scary looking, but this 3f2, you can notice n is an integer, so 2 minus n is a non-negative, sorry, is a non-positive integer. This is just a polynomial in S. Sorry? Oh, okay. I see. Yeah, well, it will be a polynomial whose degree will grow by 2 every time you increase n. And this Es star is this Eisenstein series. So it's defined as a half gamma of S sum over Mn not equal to 0, 0 of y Mn of tau to the power minus S. And this has an analytic continuation where this is the same as E1 minus S star of tau, where additionally these y Mn of tau are defined to be pi divided by tau 2 m plus n tau modulus squared. So now this object is mathematically certainly very well defined, and we can now ask what type of resurgence properties, if any, it has. So at finite n, what you find is if I draw this S-plane, where this spectrum, sorry? Yes. So it's just the standard m plus n tau to the minus 2s, right? In the Eisenstein series, it's just m plus n tau to the minus 2s. Yeah. So there's a pi over tau to n plus n tau to the minus. Yes. It's just the standard definition. So what you find is what you're integrating is over 1/2, and then you have a bunch of poles at 1, 2, 3, 0, -1. So this is the S-plane. So a natural thing you might want to do is move the contour all the way to infinity and pick up the residues from these things. So what this will do, let's pick the simplest case. If I pick C2 of tau, I find that this gives me an infinite series. So there's 1/4, which is a sum of two things. It's this C2, but there's also a contribution coming from the Eisenstein series E1, and they happen to sum up to 1/4. And then there's a half sum, k equals 2 to infinity, -1 to the k plus 1, k, 1 minus k, 2k minus 1 squared, ek star of tau. So now we've generated a formal series. This doesn't converge for any value of tau. And what we want to do is we want to resum it somehow. And a natural way how to do it is to use an integral representation for the Eisenstein series. So it goes like this. And there's a -1, k plus 1, k, 1 minus k, 2k minus 1 squared times an integral. Oh, sorry. There's a gamma function there, yes. Okay, anyway, so you now substitute an integral definition for the Eisenstein series of tau, t to the power k minus 1 dt. Okay, so this is just some formal manipulation. K minus 1, sorry. Yes, sorry, so there's an e to the minus t times y mn of tau at t to the power k minus 1 dt. Yes. So this is just an integral representation for the Eisenstein series. So what you notice now is you can commit the unforgivable sin of exchanging the integrals and the sums, and you can now do the sum over k. And after a while, you find that actually both of these terms unify into single one, and you are left with a very nice expression, which is 1/2 integral 0 to infinity. So this is this same integral pulled out. Still this sum. Actually, let me write it a bit differently. There's a 9t minus 30t squared plus 9t cubed divided by t plus 1 to the power 5, sum mn excluding 0, 0, e to the minus t ymn of tau dt. So what we have basically obtained now is a new representation. So this is now, again, a completely fine convergent representation for tau. We started with a formal series. And indeed, this is actually just a representation for C2 of tau. So we started with a formal series, and we ended up with something like this. And the interpretation is that this is like a Borel transform. And this is like, this piece is like an integration kernel, which in the standard application was just e to the minus t divided by x. What you'll notice is that over here, you don't have any singularities on the positive real axis. So this integral was fine. So this is kind of like the simple application of resurgence where you don't get anything. Yeah, where there is no resurgence, indeed. Yes. And then if you repeat this for C3, C4, C5, any C finite, you'll find the same thing. You can exchange it, and you find another lattice sum representation for the correlator, and there's never a singularity. But all of these recover the right thing. But fortunately for us, the integrated correlator is very generous, and if we study it at large n, we find that the situation is radically different, and we get singularities. So let's now turn to that. So first of all, if you stare at this formula, you will very fast realize that it doesn't really have a very nice large n expansion because it's a polynomial, and each time it's a different polynomial. How do you expand it? So really, you need to start by rewriting this whole thing in a fairly different way. And the way it's done is as follows. So there's still the constant overlap, but now there's a different integral. And this one is a bit more complicated. There's a 2 to the 1 minus 2s, 2s minus 1, gamma of 3/2 minus s, divided by square root of pi, gamma of minus s, integral 0 to 1, t to the power s minus 3, 1 minus t to the power n, 2f1 of s minus 1, s, 2s, t, dt, es star of tau ds over 2 pi I. So quite considerable effort to get from this one to this one, but this one has a well-defined large n expansion. And if you do the computation, what you now find is basically you get poles from this gamma 3/2 minus s. So you now have a poles at half integral, Eisenstein series, and you find this object has the following expansion. So Cn of tau may be written as a formal series, n squared over 4 plus a sum, r is 0 to infinity, n to the power 2 minus 2r times some perturbative piece of n and tau. And of course, the observation here is that really from this integral representation, you generate something which looks very much like a genus expansion. And in particular, these phi p of r are again formal power series, but they're this time a bit different. So there's some k is 0 to infinity, some b r comma k, n to the minus 3/2 minus k, e star 3/2 plus k of tau. So they're now half integral sums of Eisenstein series, and these coefficients b, r, k have the property that they grow like k factorial for fixed r. So notice that this is worse convergence than what we had in the finite case. In the finite case, it's polynomial in k. Over here, it's exponential in k. So it's worse. And additionally, we find that what I will now define to be the Borel transform has singularities on the positive real axis. So the situation is significantly more interesting, as might be expected, because I guess the large n limit corresponds to string theory, so you expect all kinds of interesting things to come about. So now the real question really is, of course, what do we do with these series? How do we resum them? How do we define Borel transformation, resummation, and so on? So I will do this. So really, if you remember at the start, we had the first step, which was a formal power series in X. Here it's a formal power series in Eisensteins. The second step, we want a Borel transform. So I define B of this phi perturbative R and T to be the sum. K is 0 to infinity. This B RK gamma K plus 3/2 divided by gamma 2K plus 3 2 to the power 4K plus 5 T to the power 2K plus 2. Okay, so this is a very idiosyncratic expression. Where did I pull it out of? But it's actually almost uniquely fixed by two requirements. First of all, it must come from an integral representation, some integral representation of the Eisenstein series. So that's the first thing you need to do. And second of all, it needs to cancel the k factorial divergence, which you have from there. Notice that there is, of course, a k and a 2k, so it's canceling off the k factorial divergence. And this power of 2, it's an arbitrary choice, but it turns out if you introduce these additional factors of 2, you find that if you take this function and you consider the t-plane, this is a definition, but it comes, of course, it originally comes from some kind of insight you have about what it is that you want to do. But this is a definition, yes. But the reason for this definition is that the Borel transform has the following analytic property. It's analytic in the unit circle, and it has branch cuts at +1 and -1, which are logarithmic branch cuts, at least for all of these observables. And then finally, so we have a Borel transformation. What we want to do finally is we want to define a resummation. And the resummation is S theta of this phi p r of n and tau. And it's simply given by an integral 0 to e to the I theta infinity of the Borel transform, which we defined in the previous step. And then there's an interesting integration kernel, which is epsilon root nt and tau dt, where this is a modular version of an exponential. I will define it in a second. So this is like this. And epsilon of t and tau is defined to be a sum over mn, excluding 0, 0, of e to the minus 4t square root of ymn of tau. Yes, so the resummation, this is still a directional Laplace transform, but the integration kernel is different. In particular, it's a modular function of tau defined this way with this kind of maybe slightly odd square root of ymn sitting. Indeed, yes. But I'll return to that in 1 second. But there is, of course, a final step, because this S theta now depends on whether I go above or below the branch cut. So I need to complete the final step, where I really need to define a trans series equivalent for this. And this trans series now depends on sigma n and tau, and it still has this perturbative piece. And it has a sigma times a non-perturbative piece. Where the non-perturbative piece is given by a sum of precisely the functions dn which appeared in the beginning. So it's a sum from k equals minus 3r minus 1 to infinity. Some coefficients d, r, k, n to the minus k plus 1 divided by 2, dn k plus 1 over 2 tau, where dn of s and tau is defined to be a sum over mn, excluding 0, 0, of the exponential of minus 4 square root of n ymn of tau times 16 ymn of tau to the power negative s. So the point is, if you now define a resummation for this total thing, the same way how introducing a non-perturbative term proportional to e to the minus c divided by x, I can now introduce a function involving these dn's, which will then have a non-ambiguous resummation by shifting this value of sigma. And indeed, so you said that there's a theorem that remains to be proved that what I started with has anything at all to do with this object. I don't profess to have a theorem in general, but at least for the smallest one, it really can be made very rigorous. So if we consider this first of these objects, so it was this phi p0 of n and tau. So this was, if you find the coefficients, it's minus 2 divided by pi times the sum k is 0 to infinity 1 plus k squared gamma k minus a half gamma k plus 3 halves gamma k plus 5 halves divided by gamma 2k plus 3 and to the minus 3 halves minus k e star 3 halves plus k of tau. From this you can define the Borel transform, which actually turns out to be very simple, far, far simpler than this original sum. It comes out to be simply minus 6t squared 2f1 minus a half 5 halves 1 and t squared. And then there's a mathematical theorem. You can start with the contour integral definition for the spectral representation. So you have this function c0 of tau, which is the leading leading tau dependence, leading modular function. In large N. And then what you can show rigorously is that the C0 of tau really is equal to a half times the integral 0 infinity plus I epsilon integral 0 infinity minus I epsilon of this Borel transform. Epsilon t square root of n tau dt. And basically the way you prove this, so this is just a statement. I can manipulate one contour integral, the one I start with the spectral representation. I do a bunch of changes of variable movements, and I end up with this contour integral representation. So this is just a result of complex analysis. Yes, exactly. So this is the median resummation. So of course, this is just a result in complex analysis, but the reinterpretation, of course, is completely different. This is the median resummation of the perturbative series phi p0 of n and tau. Yes, so this kind of answers partially the second question, which is, does modularity, at least in this particular case, it really enforces a version of resurgence, because really you can derive the median resummation starting from the contour integral representation of the spectral theory. And just a final remark, and in a second I won't say anything much more. Remember I was talking about all of these different limits you're interested, where you send n to infinity and something plus tau 2 of n. So, so these are the different limits, the very strong coupling limit, the toothed limit, and the dual toothed limit. But notice that the only dependence on both n and tau really comes from just this function epsilon. So really, all of the kind of dynamical information about the theory is absorbed in here, and there's no dependence. So really, you get access to all limits of interest just from this epsilon function. Sorry? Yes, yes. Yes, exactly. The Laplace transformation. Yeah, so I believe I've run out of time, so I'll end with this. Yes. Yes. Mhm. Mhm. Yes. Mhm. Absolutely. Yes. Mhm. Yes. What have I gained? Well, it's easier to split it up into different pieces. So over here, you have a very explicit expansion in terms of the perturbative piece, which you can, for example, in this case, identify in physics with these, for example, higher derivative corrections to supergravity, which were these Eisenstein series E3 halves, E5 halves. But then you additionally have these new objects, which are these dn's of k plus 1 over 2 tau, which are these non-perturbative completions. And these, again, of course, have some kind of interpretation, as they could be some kind of d-string instanton and so on. So it's really the splitting up into a perturbative and a non-perturbative piece, which this procedure kind of allows you to see much more clearly. That's you're asking about the non-holomorphic cusp forms. Yeah, I mean, I don't know. I mean, over there, in principle, you still have an infinite sum. Maybe you can somehow deform the sum and do resurgence on it. But as far as I know, there's certainly no analytic results that you could do with these things. And in this case, fortunately, these overlaps vanish, so there wasn't a problem in order to analyze this. Yeah, maybe. Um, mhm. Oh, yes. Mm. I mean, well, that's a very interesting question. I mean, when I started the talk, one of the things which I mentioned at the start was the appearance of these functions dn also in other contexts. In particular, there is this paper where they discuss just on model compactified on a torus. And I guess maybe that has some relation to condensed matter physics, arguably, and these same types of functions appear there. I believe over there, they, at least within the context of the paper, they come about through a different means. They don't do this type of resummation. But whether or not this has some type of clear connection to condensed matter, I really wouldn't be able to say, but it's possible. Uh-huh. Yeah, yeah. I mean, it was really forced when you went from the finite n to the large n. It's just the fact that this new function, this new spectral overlap, kind of got way more complicated, and it had this gamma 3 halves minus s. So yes, I certainly didn't choose it. It was because the poles over there, you have your integration contour, and they're now at 3 halves, 5 halves, 7 halves, and so on, which is different. So yeah, it's not a choice. And putting the square, and also, the reason there's a square root in this modular exponential function really comes from the factorial divergence. For example, if BRK went like k factorial squared, you would find that you need to put a cube root over here. So basically, the functional dependence is really fixed by the growth of these coefficients. So the square root really comes about because the because the formal series has factorial growth. When it didn't have factorial growth in the finite n, it was just ymn. So this is fixed by that. No, 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 no. It could be. I'm saying it could be. In here, BRK is Jevry 1. That's why it's a square root. It's the square root is fixed by Jevry 1. Yes. Ah. Yeah. Well, I mean, another obvious thing that you could do over here, well, yes, you're right. You can introduce these epsilon parameters, which will characterize a squashed sphere. And over there, I think the situation is much harder. And in particular, I guess, because you eventually return to the super conformal case, a squashed sphere probably is the same in the n equals 4 theory as a non-squashed sphere. But I'm not going to make a claim about that. But another obvious thing you could do, you could do m derivatives here. As I said, it's an even function of m, so you could take 4 m derivatives of log zg. And this does indeed give you a new observable. This observable is much harder than this one. For example, for this observable, the spectral representation isn't known yet. And but this observable is very interesting over there. It's actually not Eisenstein series, which appear in the kind of expansion. It's these things called generalized Eisenstein series, which are a solution to a certain differential equation. And this, for example, gives you access to the D6 R4 correction to type 2B string theory. So over here you had the D R4 and D4 R4. For this, the fourth mass derivative, you have this new correction, but it's much harder. I see. I see. Uh-huh. I see. Yeah. I see. Yeah. Thank you. That's very interesting account and connection. Oh, these DRKs. Yes, I can write. There's a generating function for, so they will be determined by the singularity structure of B phi PR. So this B phi PR has a singularity at 1. So what you do is you expand this function around the point 1, and then the generating series will give you the coefficients DRK. I can give you just an example for the lowest order. You find the following. So you see that phi 0, non-perturbative of n and tau. It starts with minus 2 dn 0 and tau, which comes from the pole part. But then there's an infinite sequence. K is 0 to infinity, d 0k, dn k plus 1 over 2 tau, where these coefficients are generated by minus 9, 1 plus t squared, 2f1 minus a half, 5 halves, 2 minus t, 2 plus t. This equal to the sum, k is 0 to infinity, d 0k over k factorial, t to the power k. So you match, you expand the hypergeometric in the Gauss series, you match whatever you get here, and you can find them. But they're far, far more complicated than the BR case. The BR case, you can really find a very concrete formula for it, just in terms of some gamma k over gamma k. Over here, it's really seems to be quite a complicated generating series. Equals. So this 2f1 is just a generated 2f1 at minus t2 plus t is a generating series for these coefficients. It's possible they satisfy some recurrence relations, but I haven't been able to find any. In particular, there's also an interesting question about what happens with what happens in the large n limit, because in the small n limit, there's a recurrence relation which fixes Cn in terms of C2. You can ask, is there some kind of an equivalent which fixes this CR, where you study these genus expansions? But over there, as far as I know, no one knows whether there is a recurrence relation between them. There's very curious connections. For example, if you take the coefficients BRK, so if you take these BRK, what you find is that you can analytically continue to negative K. To K less than 0, which is, from the series perspective, meaningless. But you find that at a higher genus, so if I go, for example, at genus 2, you find that at negative values of k, you recover genuses 1 and 0, sum of the coefficients. So analytically continuing at higher genus somehow gives you coefficients from lower genera. But I don't have a concrete explanation for why this is the case. Maybe, or something like that. Yeah, I mean, this has a nice interpretation of the 't Hooft limit, because in the 't Hooft limit, it turns out you require a finite number of terms from these lower genuses. And these precisely correspond to that. But from the spectral representation perspective, this is very, very non-obvious that these coefficients have this property. The case sum. What do you mean, the case sum? The DR case. This one? You can define, there is a way how you can define a resummation for this thing. This series also diverges because these coefficients drk also grow like k factorial. But you can define a resummation for it, and this resummation will once again have poles. So presumably you can continue the resurgence procedure and analyze it at other poles. Oh, you mean, exchanging these sums? I haven't thought about that. Yeah, I'm not sure. That might be possible. Uh, but yes, I won't comment on it for now.